The next talk is given by Erik Waingarten and is about the Johnson-Lindenstrauss Lemma for clustering and subspace approximation.
Okay, thanks, Vincent. This on? Yeah. All right, first I'll thank the organizers for inviting me. And this talk is joint with Moses Charikar. I guess I want to convince you that even though you've probably all used the Johnson-Lindenstrauss Lemma, there's still a lot of things that we don't understand about it. And I'll highlight some of the new results as well as the open directions. But okay, so that we're all on board, oops. Let me just start out with the statement of the JL lemma. Is this probably Jelani covered it in the summer school? It's a statement about high dimensional Euclidean space. It says that if you have X is any set of n vectors, and these are d-dimensional vectors, there exists a map pi, and pi maps RD to RT, where t now is just log n over epsilon squared. So it doesn't depend on d at all, and logarithmically in n, such that for any two vectors in your original set X, the Euclidean distance between X and Y is up to 1 plus or minus epsilon preserved by after applying this map pi. Right? In fact, we know a lot about this map. In fact, we know explicit constructions. You can sample, say, a matrix, a T by D matrix, where each entry is an independent Gaussian of variance 1 over T. If you sample that, then for a fixed set X with very high probability, T being set to log n over epsilon squared, it has the sort of JL guarantees. So now there are other maps for which this works, but for the rest of the talk, let's just focus on this map. Whenever I say JL, I really mean just sample a T by D random Gaussian matrix. All right, so our motivating question is really, when can we use the Johnson-Lindenstrauss lemma as a general tool for reducing dimensionality, going beyond just pairwise Euclidean distances? Or more formally, I guess, you have a computational problem, and this problem lives in RD. We'll talk about clustering and subspace approximation. Can you just, even before you begin to talk about algorithms, sample a Gaussian matrix, reduce the dimension to dimension t, and solve the problem in the lower dimensional space, and that gives you an approximately optimal solution to that of the original space? Or more precisely, how large does t need to be such that you preserve the cost of the optimal solution up to a factor 1 plus or minus epsilon? All right, I want to give two examples of two different kinds of problems that will really highlight kind of why this is interesting and something new is happening beyond the usual JL guarantees. So here on the left are two sort of Euclidean optimization problems. On the left is the one median problem. If you've heard of, say, the K median problem, this is a setting of K equals 1. And on the right is the one medioid problem. And the one median problem says the following. You receive the data set, x1 through xn. These are d-dimensional vectors. And what are you trying to minimize? You're trying to find a point, a center point C. And this is an arbitrary vector in RD, such that it kind of is a center among the points. So it minimizes the sum of the distances from each data set point to that fixed vector C. Okay, now the medioid problem is very similar, except that C can't be arbitrary. It has to be one of the n data set points. All right, so the picture for these two problems is the following. On the left, if you were to optimize over C, you expect Z to be somewhere in the middle. On the right, C is constrained to be one of the points. Okay, so now the question is, can you apply Johnson-Lindenstrauss at all? I claim that for one of these problems, it's a fairly simple application of the JL lemma. For the other problem, it's actually not even clear that you can apply the problem at all. Anybody have any guesses? Which one is easy, which one's hard? Right, so the medioid problem is simple application. You can reduce to log n over epsilon squared because the center is one of the n data set points. So really, this problem is only about n squared many distances, and you can union bound over the n squared many distance. However, on the right, on the left, this problem, the center, can be infinitely many points. You can't hope to union bound. Oh, and actually, let me say that this log n over epsilon is actually tight. There exist simple examples for which you really do pay this log n factor. The problem on the left is much different. Nevertheless, I'll show you that you can actually do much better than the usual Johnson-Lindenstrauss guarantees In fact, you can get bounds on the dimension t, which are completely independent, not only of d, but also n of the number of points. All right, so that's the first problem. Let me tell you a similar problem, but this is the subspace kind of approximation problem. On the left, we have the one subspace approximation, and it looks a little bit more complicated. Again, you start with a data set of n points, and that green point, that's my origin. And what do you want to do? You want to approximate the data with a one-dimensional subspace, so a line. Was there a question? Okay, so you want to approximate that data with a one-dimensional subspace. And what do you pay for? You pay for the distance of all the points to the nearest point on the subspace or to its orthogonal projection. All right, so that's the picture on the left. Right, you're picking that line which minimizes the sum of the black lines. On the right, it's the one-column subset selection problem. It's basically the same as before, except that now your line has to go through one of the n data set points. Okay, again, you get a similar situation where for the one-column subset selection, it turns out that you can reduce to dimension log n over epsilon squared, and that this is tight. However, the techniques I'll give you can show that it's completely independent of n, and you can actually reduce to dimension 1 over epsilon cubed, or at least that's the bound that we can show. All right, so this is the outline for the rest of the talk. I'm going to tell you more precisely what are the problems that we're going to study and some of the prior work. We're not the first to ask this question. And then I'll go into, I really want to tell you this one technique, this one idea we came up with, and can really handle all these problems, maybe not in the optimal way, but it gets some non-trivial bounds for them. And then I'll conclude with some open problems. All right, but before we start, let me just tell you the conceptual takeaway message. This talk is about understanding the Johnson-Lindenstrauss transform. And even though it's not about an algorithm, I'm going to use algorithms for constructing what's known as core sets for these problems. I'm going to tell you what core sets are, in order to use these algorithms as an analytical tool in studying what happens when you apply a Gaussian matrix. All right, so that's the takeaway message. By the way, if there are any questions, feel free to stop me. Yeah.
Actually, yeah. When you talk about, say, like using JL to like solve median, like, I mean, sure, you can like project everything down to a lower dimensional space, and you can compute the median in this lower dimensional problem, but can you then somehow relate that back to the original median in this higher dimensional space?
Yeah, that's a good question. When I say, I guess for this talk, when I say preserve, I mean the cost. So I want that the cost of the optimization, if you pick the optimal median in the projected space, it corresponds to the cost of the optimal one in the original space.
Okay, so you use it to approximate the value of the median.
That's right.
Not necessarily the point itself.
That's right. I mean, yes. Cool. All right. So let's get more into details or what the problem definitions are. The first one is the KZ clustering problem. I talked about the one median problem. I'm going to generalize the 1 to k. And then instead of taking sums of distance, I'm going to take the sums of zth powers of distance. But the idea is now that we have a data set. And now what do you get to do? You don't get to pick just one center. You pick k centers. And again, these are arbitrary points in RD. And now what are you trying to minimize? Well, you're going to take the 1 over zth power, or the zth norm, of the sum from each data set point to its closest center. Right? This is k clustering problem. The case of z equals 1 is the median. Z equals 2 is known as k means, or z infinity is known as k center. You can think of as you vary z, you're more sort of sensitive to outliers. But again, the question is, I sample my random map pi. Wherever I saw x before, I substitute pi of x. And whenever I saw RD, now I substitute RT. How does the cost of this optimization problem relate to that of the original? Okay, that was the KZ clustering problem. And now let me sort of generalize this KZ subspace approximation problem. Again, we have data. We want to approximate it with a k-dimensional subspace in this case. So what am I trying to do? I minimize over all subspaces S of dimension at most k. And now the cost that I pay is the distance from X to rho of S will be my orthogonal projection onto the subspace S. And I take the zth power and then sum and take 1 over Z. But again, this problem, as you vary Z, it's like very well studied in various contexts. So for Z equals 2, this turns out to be the low rank approximation problem. When Z equals infinity, you can think of measuring some notion of radii or width of the points. But again, the problem is the same. Wherever I saw X, I'm going to substitute for pi of X. So that's both in the X as well as the projection. And now the subspaces that I'm minimizing, they're still dimension at most K, but now they're subspaces of RT, not necessarily of RD. All right, so now the final problem is, and I'm going to combine both the clustering and the subspace approximation problem, but I'm going to restrict to one-dimensional subspaces or these KZ line approximation problem. All right, so now I have my n data set points, and now I want to partition them into K parts, and for each part, pick the best one-dimensional subspace or the best line to approximate it. So what's the cost? Well, you minimize over the choice of K lines, and then you sum over all the points from xi to the orthogonal projection of xi onto the closest line. All right? And this is known as more generally as what's called projective clustering problem. It doesn't have to be a one-dimensional subspace, but our results will only kind of be interesting for the case when you pick lines. All right. Are there any questions on the problem statements? All right, cool. So like I said, we're not the first to ask this question. But if you look at the literature on these problems, and even in dimension reduction, but more generally in solving these kinds of questions, there's a big difference whether you choose this parameter z equal to 2 or general z. And the reason is that for z equals 2, you're taking kind of sum of squares of distance. They're kind of algebraically nice. In a particular way, it really makes our algorithms perform much better, and the analysis for these works to be much simpler. In fact, this line of work specifically for dimension reduction, it initiates with this work of Boutsidis, Soussias, and Drinias. They were the first to ask the question, what happens when you take JL to K means? And over the years, it's been improving to the fact that now we have bounds of this paper by Makarchev, Rajenstein, who proved a log K over epsilon divided by epsilon squared. And for z equals 2, for the subspace approximation problem, like I said, this corresponded to the low rank approximation. There's this paper by Cohen, Elder, Musko, and Pursue, who showed that you could reduce to t being K over epsilon cubed. All right, so now when you move to general z, you kind of lose this algebraic niceness of the structure. In fact, we don't have super good characterizations of, say, what the optimal center would be or what the optimal subspaces would be. And so much less is known, but still this Makarchev, Rajenstein paper, they actually can show something. They show for general z, you get basically a factor of z log 1 over epsilon plus z squared. The specific bound is not so important. And for KZ subspace approximation, there was a bound that was known, but it does have the dependence on n. So they were getting zk squared log n over epsilon cubed. Right? So basically the techniques that I'll be able to show you, this connection to core sets, they'll pretty much recover the bounds for KZ clustering. I mean, there's a small parameter in which we improve this factor of z. But for KZ subspace approximation, we'll actually be able to get rid of this log n factor, and our results will extend to this K line approximation. However, I'll lose this factor of log n. All right, the specific bounds are not super important. What I'm excited about is that this is one idea, it's one technique. It covers these three problems, kind of one after the other, and I'm getting bounds where, okay, except for the K line approximation, they're completely independent of the original dimension as well as the number of points. I don't expect these to be optimal, but even this log n factor, it was kind of interesting. Okay, any questions on the results? If not, I'm gonna move on and tell you about these core sets to Johnson-Lindenstrauss. Yeah.
So Also preserve the cost of any candidate clustering, right?
That's right.
So in these, when you talk about like preserving the cost, is it just like the optimum, or is it also like for any candidate
Yeah.
choices?
So I'll get more to this toward the end. It'll be like a specific open problem. Our techniques are, I mean, you need to parameterize the problem in a particular way, but we'll only work on getting the optimal solution. So we won't get this for all guarantee, but I'll also go more into details toward the end of the talk. Yeah. Ask me again if I don't. Cool. All right. Okay, so for the talk, actually, I told you about these problems, but we're just going to stick to the one median problem. I think already here I can highlight all the main ideas. But just to remind you of the question, we have this data set X, X1 through Xn, and I minimize over a choice of arbitrary center. The fact that it's arbitrary is important. And the question is, you sample a random Gaussian matrix, substitute pi of x wherever you saw x, and substitute RT whenever you saw RD. Can I show approximate equality for some t, which is 1 over epsilon squared? In fact, in this talk, I'll show you a bound of poly 1 over epsilon. All right. And now when you're trying to show kind of approximate equality of two optimization problems, there's really two directions to show. And I claim that one direction is actually conceptually much easier than the other direction. This is the case for all the problems that we'll study. In fact, I want to, in some sense, what's the easy direction going to say? I'm going to say that the cost after apply Johnson-Lindenstrauss, it doesn't increase too much. And I claim this is conceptually easier because if you want to upper bound the cost of a minimization problem, you just need to exhibit one solution. And the cost of that solution is an upper bound on the minimum. So now what do I want to say? I want to start of my cost in the original space and show that the cost times 1 plus epsilon is at most the cost of that in the projected space. So really the way to do this is kind of the first thing that you would try. You would say, okay, let me forget about the map for now. Solve the problem in my original space. Find the optimal center. Now this doesn't depend on any randomness. You gave me all the points. You could find the optimal center C that gives me the cost in the original space. And now when you sample a map, there's a natural candidate solution which you would look at. You would say, all right, where did that center map to? Let me evaluate the cost of that center and try to show that that cost is at most 1 plus epsilon times that of the original space. That guarantees that the optimization in the projected space can only be lower. And in fact, you can kind of use these basic properties of the Johnson-Lindenstrauss lemma to say that the sum from I equals 1 to n of xi minus c, this distance, times 1 plus epsilon is bigger than the sum of pi x minus pi of c, where it was important that c didn't depend on the randomness at all. Now, I want to make kind of, it's clear, but it's maybe a subtle point. It's important in the argument that I'm not preserving every distance xi to pi of c. I'm understanding the entire sum, and I'm saying in this distributional sum, can I show this 1 plus epsilon, which is different. I don't need to union bound over these n many distances. All right, but that's pretty straightforward. Why doesn't the same argument hold in the opposite direction? Well, the problem is that I would want to do kind of the argument in reverse. I would want to start with the optimal solution in the projected space RT, and then construct a solution in the original space whose cost is not much higher, that guarantees that my cost in the projected space could not have gone too low. Okay, but there's a problem here. And the issue is that when you solve for the optimal center in RT, well, this optimal center actually depends on the randomness of the map, right? If you like to think of adversaries, think of the fact that you're going to sample this random map, and the adversary is there's going to be some distortions. Potentially, you could take advantage of these distortions and find a center which happens to get distorted. Bam, that one is the optimal center, and now you kind of lost. You can't apply the distributional properties. So that's the main idea. You just, by fixing the optimal center in the projected space, since that depends on the random map pi, you can no longer use the distributional properties of the Johnson-Lindenstrauss to kind of peel that center back into the original space, right? That's the kind of the technical challenge, and that's where the core set constructions are going to let us get a handle on what these optimal solutions look like. All right, cool. Okay, so let me tell you about core sets, or this technique, which I guess it's hard to see, but I think of really as a way of doing data set reduction. Right now, if you don't like my explanation today, Vincent's talk tomorrow is going to be all about core sets, so I can go more into detail. But this is really an idea to say, all right, dimension reduction, this helps with my dependence on D. How can I reduce my dependence on N? And Agarwal, Harpalet, and Bharadarajan, they were studying the following kinds of ideas. They said, maybe I can have an optimization problem where I start with my original data set, and now I run a simple algorithm to find a smaller weighted data set, such that the cost of the optimization in the smaller data set would be approximately that of the original data set. And if I can do this algorithm, if the algorithm is simple and reduces the size of my data set by a lot, then I'll be able to gain in the computational complexity of this problem. All right, so we're going to use these ideas to analyze dimension reduction. And the good news is that for this one median problem and for all the problems that I'm going to talk about, these core set constructions have gotten incredibly sophisticated, and they can say things that are kind of surprising. So even for the one median problem, there exists a simple core set. So there exists a way to find a subset of my points, S. And for each point, I'm going to attach a weight. So the weight will be W. And now the size of the core set is only poly 1 over epsilon. So it's completely independent of the dimension and completely independent of N, is just a constant number of points, such that if you found the optimal center for that point, then that would approximately be an optimal center for the original entire data set. Right? So now the one thing I want to stress is that when you have a core set construction, it says something pretty nice about your optimization problem. Like the message is that you look at this minimization, it's a sum over N things. It looks like it depends on all its data, but really it doesn't. Now we know that this Johnson-Lindenstrauss, the underlying dimensionality, depends on this factor of N. Well, if we can only replace that N with really what the size of the core set is, we would be getting more aggressive dimensional reduction, and that's what we're going to do. Okay, so with that said, let me tell you the kind of the proof diagram, or how am I going to use this idea of core sets to analyze the Johnson-Lindenstrauss lemma. And again, I start with this data set. I want to apply pi, understand what's happening to the JL data set, but I don't know how to take this arrow directly. Remember, I wanted to peel back solutions in the reduced space to that of the original space. But what I just told you about, a nice tool, I'm going to run my core set algorithm and reduce my size of the data set to M points, M weighted points. Okay. The good news is that once you apply the core set, now you can look at, okay, what happened? What's the JL'd core set? So I look at pi of the core set points. And now remember, M is poly 1 over epsilon. So really, what I'm going to hope is that this entire subspace is just a constant number of points. This entire subspace is preserved by taking Johnson-Lindenstrauss. In some sense, if I look at points on the left and the bottom, and points on the right and the bottom, distances are always approximately the same, even if you take linear combinations of them. All right, so we're not entirely done, but it would be great if you ran your algorithm on the left. You ran the core set algorithm on the right, left. How do you run the core set algorithm on the right? If the JL core set was indeed a core set of the JL data set, then we'd be in business, right? Then we'd say, all right, let's start with the optimal solution to the JL data set. And if this diagram commuted, then I look at that solution in the JL core set. And by the fact, if the thing commuted, that would be approximately the same. Now I can move to the left because I'm a subspace embedding. So I can talk about a concrete center to the original core set. And because this was a core set, it allows me to say that that core set has approximately the same cost for the entire data set. All right, so that's the plan. I'll tell you kind of a few kind of technicalities that come up and how you can design or why these core set algorithms should commute. That's something that kind of we need to prove. But what was the goal again is just to start with a solution for the optimal JL data set and kind of follow the arrows relating to solutions of the JL core set, then to the original core set, back to the data set. And that will give me a way to upper bound the cost of the optimal solution in the original data set with respect to that of the optimal solution in the JL data set. Okay? Any questions on the high level plan? All right, cool. So let's do it specifically for the one median problem. I'm going to think of sampling my map pi. And I have this issue of like not wanting to talk about the optimal solution until, so I can still use the distributional properties of pi. So what am I going to do? I'm going to fix some success event. I'm going to fix a success event. And as long as this event holds, then I can follow the arrows while only decreasing the cost. All right, so my success event, one, is that my core set algorithm, it produces a core set, SW for RD, that's kind of the prior work, but also that it commuted, so that pi of S is a core set for pi of X. And there's one more thing I said, that I wanted that JL, the Johnson-Lindenstrauss map, was a subspace embedding, but now only from the span of the core set to the image of the span of the core set. And this is where I'm going to pay T being the size of S so that I have this subspace embedding with high probability. All right, but now S is just poly 1 over epsilon. All right, so once those, imagine I sample pi, I run my core set algorithm, and I have this success event holds, then how does the argument work? Well, now I find the optimal solution. And because I have, if I had a core set pi of S and it commuted, then if I look at the core set points, then the cost of that same solution is approximately the same. So now I can find the optimal center for that fixed core set points. That is only lower. It also takes me into the span of these 3 points. And now that I'm in the span of these 3 points, in some sense, I can look at the subspace embedding and find that corresponding center in the original space. And now those 3 points were also a core set of the original data. And this allows me to relate it to that of the entire data set. All right. Now, maybe one kind of minor thing that we'll use shortly was that I actually used a slightly weaker property of core sets. My argument just had to say for the optimal solution, when you sample the core set, the cost of the optimal solution on that core set is approximately the same in the entire data set or the JL core set. It's slightly weaker than having, it's kind of one direction of the core set constructions. Okay, so really the final step is just to argue that, in fact, the diagram commuted. That if I run a core set algorithm on the left, I apply JL, it's really the same as having run the core set algorithm on the right. And for that, I need to tell you how these core set constructions work. And at a very, very high level, these core set constructions work by importance sampling. Right? So we're going to start with our entire data set. And what I want to do is I want to define a sampling distribution. And so I'm going to assign some importance to each point, it's important sampling. If you've seen like leverage scores or even effective resistances, some notion of importance to every edge or to every point. And now I'm going to say, look, for each center, this distribution gives me a low variance estimator for the cost. So if I sample from that distribution, I would approximately preserve that fixed center. And then I need some argument to union bound over all potential centers. All right, I'm not going to go more into details of this importance sampling because, in fact, we're just going to use the black box application, modulo step 2, but we won't need to union bound because we only need it for the optimal solution. Anyways, all right. So let me tell you what is this important sampling distribution? What do you need? And you basically assign the following importance. If you look in the literature, these are known as what's called sensitivities. It's basically some measure of saying what fraction of the cost does each point contribute to any particular centering. And you take the worst case center. Right? So it's the supremum over all C of the distance from X to C divided by the sum of all the data set points. This denominator is the total cost to C. The numerator is the contribution of that fixed point X. And then you do the traditional importance sampling approach where you sample X with probability proportional to the sensitivity. And now the weight should be set to 1 over kind of the probability such that in expectation you get what you want. Right? So in some sense, the union bounding over all potential solutions, I'm not going to go into it. Probably Vincent will cover it, hopefully. But this is really a black box application. On the left side, we can just sample a core set. This thing will be a core set. All that we need to do is argue that the optimal solution on the right-hand side is preserved if you looked at the core set. All right, so this is going to be straightforward. If you look at the optimal solution, this green point, well, we set up the sampling distribution such that, and this is true for any distribution, in expectation, if you sampled the core set, then the cost with respect to the core set would be exactly that cost of the optimal solution. So at this point, you can just use Markov inequality. Right? You can say, well, OK, with probability 99%, this is only a factor of 10. But now we have something cool because we can kind of say that JL preserves up to a constant factor with probability 0.9. Right? In fact, these are the arrows. We start optimal solution, we go down, we lose a factor of 10. Then from going from RT to RD is a factor of 1 plus epsilon because of subspace embedding. And now on the left, this really was a core set. So here we only lose a factor of 1 plus epsilon. All right, so we've shown that actually a very simple argument, JL preserves the cost of the optimal up to a constant factor with probability 0.9. But I promised you that was kind of what I just said. I promised you that we could show a 1 plus epsilon guarantee. And the first step was to apply Markov inequality. So really, I just want to upgrade this and use Chebyshev. So I just need to upper bound the variance of the estimate in the optimal solution. All right, so maybe this is where the paper gets a little bit technical, because what do? Well, I said, well, if I could have sampled from the true kind of sensitivities in the projected space, I would have written down the same kind of sigmas applied to pi of x. And I want to say, can I show that on average, sigma prime, or what I would have done optimally, is up to a constant what I actually did, right? Because the algorithm depends on the original representation. But now, it's a little bit technical to show that, but we have something new that actually the optimal solution is preserved up to a constant factor. In fact, the argument can lose constant factors here, because then I can just decrease the variance by sampling more points. All right, so this is kind of a summary of the slide. What I find cool is that I gave you pretty much the entire proof, and I almost didn't really talk about clustering. In fact, the same proof works for subspace approximation and for the KZ line approximation, modulo thinking about what it means to preserve. Like, do I need a subspace embedding, or what exactly do I need there? But are there any questions? That's basically the technical content, and try to have a few open problems. Yeah.
So what breaks down for the medioid?
Right. So for the medioid, this core set, it doesn't commute. It turns out that the core set constructions, they're actually much more powerful than what I just said. So I just said that the cost of the optimal solution is preserved. It turns out that with core sets, because you're union bounding over all solutions to some extent, you can preserve the cost of any centering. However, I can't prove this theorem because it's not true. So the core set of the JL core set is not a core set of the JL data set. So it's not true that for the medioid problem, this diagram commutes. Yeah. Why is the dependence? Oh, in the KZ line, but yes. So yeah. So I did say that the core set constructions are incredibly sophisticated. For the K-line approximation, there is a dependence on n, and it's exactly logarithmic. It's like logarithmic in, it's log n to the k. So this whole framework, I was pretty loose, but if you tighten it up, it turns out you end up paying essentially log of the core set size. And since the core sets for K-line approximation have this dependence on n, then on log n, then we get this log n factor. It's still an open problem as far as I know. What are the best core set constructions for K-line approximation? For all these problems, I think there's been a lot of progress on the clustering problem, but definitely not as much on the subspace approximation problem. All right, any further questions? Okay, cool. So let me just conclude with some open problems, and this will address the problem that you brought up. It turns out that there's a slight difference here when you talk about for all guarantee, or what you could hope to show, and that of preserving the optimal solution. Because for some of these problems, for the clustering problem, I asked the question of finding the optimal centers, so finding k points, such that the distance to each center is minimized. You could also parameterize the problem and say, okay, find the best partition of points into k parts, and for each part, find the optimal solution. So you could ask, and it turns out that these papers, McCarter, Rajenstein, and I think Burry, Becchetti, Cohen-Haddad, Grandioni, and Schwigelson, they can prove these kind of guarantees. They can show that for clustering, for any partition of your data, then if you find the optimal center for that partition, the cost is approximately preserved for all potential clustering. This is much stronger than what we're showing. And yeah, I mean, I still don't really understand what the kind of, there is a minor difference in talking about centers and talking about clusterings. For the optimal, they happen to align, but yeah, we still don't, I mean, for the KZ line problem, we don't know how to prove these for all guarantees. So that's also a great open question. Or in general, is there any difference, or what is the difference between these? All right. The second open problem, and maybe this is much more general, is that I really like this this kind of idea, or this a very simple way of avoiding the so-called curse of dimensionality, right? We haven't talked about algorithms, just sample a random map, reduce the dimension. It's really nice when we can show, or we can understand what is happening for these problems. So we talked about clustering, subspace approximation. There's been this recent line of work showing some bounds for the problem of facility location or single linkage clustering. I think some folks here from MIT, as well as for the Wasserstein barycenters problem. There's still a lot more questions to ask. Like you can ask the opposite problem of, for like a particular dimension, what is the approximation that you get? Say if you wanted to project to, I can afford to 5 dimensions. Yeah, all these questions we still don't really understand. I think there's a lot of interesting work to do. But yeah, that's pretty much it. I can also take any questions.
All right, any questions? So actually, I have a question. So for facility location, you can project, like, what is the work that what is this open problem that they are asking, that you're asking here?
No, I was just, this was just showing there's like a recent push to understand. I'm not saying for this specific problem for facility location, or in general, there's like, okay, for projective clustering problem, our results get stuck even for the K-line approximation. The reason is that for projective clustering, we don't have course sets with analogous guarantees. We lose like some additive error. It's not even clear that course sets are the right technique for this problem. In fact, these other papers, they proceed with completely different tools.
But they do manage to reduce the dimension to something constant here, or like?
Oh, so specifically that paper, no, they have results showing that for structured data sets or data sets with what's called low doubling dimension, then you can reduce to dimension, which is the doubling constant.
Yeah. Any other question? All right. If not, let's thank Erik again.